Welcome back from lunch. We've got another good programme planned for before now and tea. David Bowman, you're going to have...
G0MRF.
Thank you, G0MRF. I should know that. Yes. Going to talk about ESEO and lots of interesting things on board there, and I hope away you go.
Okay, first of all, testing, is the mic working? Yep, okay, thank you very much at the back. ESEO, it's a project that's been going nearly as long as me. I first remember attending a meeting on this particular satellite project in 2007. And of course, between starting on this and today, we've been involved in FunCube 1, payload for UCube, some equipment for EO79, and of course Naive 1, which is now awaiting launch. So comparatively speaking, although this is a professional project, this is a European Space Agency Education Department, it has actually taken its time. But finally, after years of coming along saying, well, we've made a bit more progress, we've written another 10 kilos of paperwork, we must be nearly there now, we actually have hardware ready to be shipped out to the prime contractor in Italy next week. That's 95% complete, but at least it's something that we can wire into a flat sat out there and check that it talks to the rest of the satellite. AMSAT-UK is providing a payload for this mission. So before I go into an overview, I just want to show you this slide, which is a rendition made by ESA on the satellite. It's got 3-axis stabilization, which is very nice indeed. And the first rendition we saw showed our L-band uplink and our VHF downlink antennas on the space end of the satellite. So nobody managed to spot that L-band won't actually travel through solid objects, and that was pointing into outer space. Fortunately, we've now got a patch antenna on the bottom pointing towards the Earth, if the 3-axis stabilization works okay, and a nice VHF antenna on the top. So it's finally coming together. Okay, so ESEO overview, European Student Earth Orbiter. There's 2 presentations on this today. My one really takes a look at the RF systems on board this satellite from an AMSAT perspective. But broadly speaking, being an educational mission, we have it listed officially as an educational hands-on project from ESA Education. In all likelihood, this will be the last major satellite they produce themselves, because obviously in those intervening years, CubeSat technology has taken over for education with a much shorter turnaround time. This is a 20-kilogram microsat. It's paid for. The customer is European Space Agency Education Department, but they have a prime contractor which started off as Alma Space, and in the intervening time, that company has now been bought up by another aerospace company in Italy called Cital. The launch for this is going to be sun-synchronous. It's actually being looked into now to find a suitable vehicle to send it up on, so we're all getting much more enthusiastic than we were a few years ago, when it looks like it was a very long way in the distance. Baseline altitude is 530 kilometers, because ESA are very, very hot on orbital debris mitigation, and that's about the maximum height we can go to and guarantee with this particular profile of satellite that it will actually re-enter within 25 years. And being sun-synchronous, 1030 LTAN, so sort of 1030 every morning, rather like FunCube, is the time it's designed to come over a particular area of the Earth's surface. 3-axis stabilized, as I said, nadir pointing. The way it works is that the universities involved, there's about a dozen universities around Europe involved in this project. They are providing science payloads for the mission and ground station facilities. And the Italian prime contractor are really using this opportunity to develop space heritage for their platform. They're providing all the onboard data handling, the EPS systems and things like that. So they're getting heritage out of it for their satellite bus, and the students are providing payloads and ground station facilities. UK participation, Cranfield University have provided a deorbit mechanism. Mechanism wouldn't fit on that line, so I just put payload. In fact, it's an inflatable ring that goes around the outside of the satellite, so that after the main mission is over, they hope to inflate that and increase the amount of drag to get it to re-enter. Having looked at it and analysed it, it won't make it happen very quickly. So this isn't one of the very large sails we saw earlier from Dr. Chris Bridges. This is simply an inflatable ring around the outside of the spacecraft, which will increase the surface area a little, but it will be measurable. AMSAT-UK are providing an FM transponder, L-band uplink and VHF down. And we're also doing the familiar educational telemetry based on the FunCube sort of standard, if you like, of 1K2 BPSK with forward error correction. But 3/4 of the way through that long period of design and consideration, they suddenly decided that all the science data, which comes down on S-band, they didn't have a backup for. And the S-band downlink transmitter is another student payload, so without that much heritage. So they got a little bit worried about that and said, can we provide some sort of backup for data transfer from the science payloads? The S-band system can do megabits per second. Our system on 1K2 would take weeks and weeks and weeks to downlink an image. So we've actually managed to implement 4K8 using the same standard, so we can command it to a faster data rate than you've been used to hearing on the FunCube satellite. Okay, so I said I'm going to concentrate a little bit on the RF systems on board. ESA are very, very cautious about anything from a group of people labelled radio amateurs. They have command and control and mission telemetry from the platform on 70 centimetres. So we have 3 ground stations looking at that: Forlì in Italy, which is Alma Space, Vigo in Spain, which is a university ground station, and a system known as SatNet, which, as far as I understand, is organised by Cal Poly, and it bears some resemblance to the Genzo system that we saw some years ago, but apparently it works, which is always a good thing. The science data, the transmitting equipment for that is on commercial bands. It has an uplink and a downlink, so it's got a full ESA-approved sort of handshaking protocol where it downloads data and then acknowledges that that's been received okay. The ground station for that is in the University of Munich, and the payload, which is dynamic, it can change data rates, it can change all sorts of different modulation formats. That is being received in Munich, and the payload's been developed by some Polish students in, I forget which university, but nevertheless, yeah, I think it's the same group who produced the patch antennas for the Columbus module. So they've got quite a heritage of communications gear. So with 70 SEMS and S-band in use, we were told that we could not use either 70 SEMS or indeed our own allocation at S-band, which is 2.4 gigahertz, simply because they didn't want anything too close to their receive capability on this particular commercial allocation, which meant that we had to go for this sort of arrangement. So we've developed a payload which is essentially a communication system with an onboard computer to do all of the telemetry gathering and processing and modulation generation. We've got a couple of L-band receivers. We'll have a look at that in a moment in more detail. One is a command uplink, so we can directly command the payload into its various operating modes. And the other part is an L-band receiver on 1263.5 megahertz, which is the input frequency for the transponder. The reason for using 1263.5 is just to keep it above the limit at which our friends in Germany have some fairly stringent power restrictions. In Germany, apparently there's been an issue with radar, interference to radar systems from amateur 23-SEMS transmissions, and below 1263, I believe the ERP limits are very, very low indeed. So we've kept it just above that. Throughout this project, a little alarm bell has been going off in my head every time I mention the uplink frequency. I see ESA people around me or on telecons, on Skype, and I keep thinking, any minute now somebody is going to say the word Galileo interference. But even though we've spoken to some of the communications experts from ESA, they seem very happy that we're using L-band, even although this falls within one of the downlink parameters of the Galileo constellation. Okay, on the downlink side, we've got a VHF system there, two different services, but only one frequency. So unlike FunCube 1, where we have a transponder mode and a telemetry stream that's able to work at the same time, because of power considerations here, we've actually gone for two different systems. So we have a telemetry downlink, either 1K2 or 4K8 on 145930, and the transponder operates on the same frequency. So we can switch between either of those two things, but we can't use them at the same time. So communication system requirements, almost predictably, educational outreach by transmission of platform and payload data. So as in FunCube, we collect all of the data from sensors within our own payload using I2C communication, which is what we've done in the past. But in this particular case, to get the more interesting educational data, for example, we aren't able to access directly things like solar panels, battery currents and voltages. We have to gather that from the platform CAN bus. So a new thing for us is dealing with a CAN bus communication on a satellite, and we have to interface that system and all of its restrictions with our own payload and grab data in from that and then format it into our telemetry stream. Communication transponder, we've already said that. It requires 67 Hertz CTCSS nominally. We have the ability to switch that off, but normally it will work rather like the other satellites we're familiar with. So you'll transmit up on 1263.5 with 67 Hertz enabled on your FM transceivers, and at the end of that transmission it will stay on for a period which we haven't quite decided on yet, but it might be around 10 seconds. Science data collection, it's back up to S-band. It's BPSK with forward error correction, just like we use on FunCube 1, but at 4800 bits per second. What this means is you won't be able to pick that up on a standard transceiver. Remember, to receive BPSK, we need a SSB type receiver. SSB receivers have filters in that stop at around 2.4, 2.5, maybe 3K. That signal will not fit through it. We would have hesitated to do that when we were designing FunCube, but nowadays SDR receivers are relatively common, and indeed we have a dashboard which can interface to an SDR receiver like the FunCube dongle, which will automatically detect the data rate and demodulate it. So you need an SDR for that particular receiver. At 4K8, I think Graham described it possibly yesterday as an angry fun cube. It is simply speeded up, so you get those little beeps 4 times every 5 seconds. And what we've done is we've interlaced 1 frame of the AMSAT telemetry with 3 frames of science data. So even although we are transmitting the science data, you still get the AMSAT telemetry. So it's 1 frame of AMSAT and 3 frames of science data in 5 seconds. Okay, there's always limitations and trade-offs in this sort of thing. And if we have a look at this, desires, so ESA will come along and say we want the fastest possible data rate, the high sensitivity receiver on the satellite, so you don't have to run too much power from your ground station, and a high signal level on the ground to give the best link margin. And we say, oh great, we'll really enjoy designing that. And then they sort of pause and say, but you haven't got much DC power, you've got a very limited mass budget, there are EMC considerations on this because we have to conform to masks, so if the spurious or harmonic outputs from our system exceed a particular limit, it will fail the acceptance testing. Limited volume budget, smallest possible antennas, and I had a conversation with somebody who said, what do you mean your VHF antenna is that big? Why can't it be the same length as our 70 SEMS antennas around the outside of the spacecraft? And I thought, you're a mechanical engineer, obviously. Didn't really understand the concept of antenna length with wavelength. But, you know, we work through these things. Also, having said lowest possible DC power consumption, one of the other requirements is that it has to include an isolated DC to DC power supply. Now, these things can be very efficient, but only if you run them up near their limits. So if you have a 5-watt DC to DC converter, you can run it at 4.5 watts and you will get 90% efficiency. But you also have to say, well, when you select something for a mission like this, you have to have an enormous margin between the rated output capability of the product and what you're actually going to run it at. So we've got something like a 10 or 15 watt version of this DC to DC power converter, but we're only running it at a maximum of 1/3 of its maximum capacity. So it remains nice and cool, but the efficiency, if you look at the curves on those things, go down dramatically if you don't push them at their limits. So I think a significant proportion of our power budget just goes in actually running this DC to DC converter that everybody has been made to put in their particular payloads. Okay, I shall walk around this side and hope the speaker doesn't get me. So here's the functional block diagram. I don't expect you to be able to see all of this, but because it's on the BATC site, I'm sure if you wanted to, you could go and freeze frame the replay and have a closer look. Essentially, the 2 blocks in green are our sort of onboard controller. It's a 32-bit version, is it, Chris? So upgraded from 8 to 32 bits to deal with all the extra work it has to do, and an electrical power system. So a command decoder, memory, forward error correction and telemetry generator all in one processor. Chris and Graham will be talking about that a little bit later. And an electrical power system with a nice big chunky DC to DC converter in it. The top blocks here, we've got a patch antenna produced by a company in this country. That's going to be bonded, glued onto the bottom of the spacecraft. We then take our L-band input and go through a low-pass filter to filter out the S-band signals, which are on an antenna right next to us. We then go through a series of preamps and surface acoustic wave filters, and quite a lot of this is new technology for us that we haven't flown on FunCube, so it'll be interesting to see how it performs in space. After the LNA here and the filters, we split the signal into 2 paths, one into a command receiver and another one down into the FM voice receiver for the transponder. So receive portion up here. On the lower portion down here, we generate signals with the forward error correction and modulation shape to go into a BPSK modulator. The output power is determined by the amplitude coming out of that D to A converter up here. That can modulate either at 1K2 or 4K8. Goes into a linear amplifier, which is essentially a copy of the one on FunCube because it's still on 2 meters, a little bit more power. And then a slightly different arrangement. We go through a Skyworks gallium arsenide switch here, and that goes through to a common low-pass filter and 2-meter antenna. The other path is the transponder, where we have the voice receiver connected to a 145 megahertz oscillator here. It's actually a phase-locked loop reference to something like a 16 meg crystal. We modulate the fundamental mode crystal there. That goes through to an amplifier which is rather more efficient because it's FM, and we can select that particular amplifier with the Skyworks solid-state switch, and then that goes through here and that goes to the output. There's also a little bit of logic on there to stop both power amplifiers being selected at the same time should the software go a little bit awry during development. So that's quite good. Okay, so circuit diagrams. Won't spend too long on this, but there's some nice technology in this. LNA, I'm just showing a couple of slides. This goes on to several different sheets. This is the down converter part of the L-band receiver. We've got a filter on the front, a little inductor down to ground to get rid of static off the antennas. Low pass filter, centered around 1400 megs. Surface acoustic wave filter there. Very nice, managed to find one from DigiKey in the USA. Didn't say I was putting it in a satellite, so didn't have to fill out oodles of paperwork and wait months. Broadband amplifier, another surface acoustic wave filter. These are centered on 1267 megahertz. Another amplifier there. And then another new device for us. It's a 3 dB splitter. It's a 90-degree splitter. It's been a year since I read the data sheet. LTCC technology, which is, I think it's low temperature co-fired ceramic. So it's extremely small, but nevertheless has very little loss. And just like the branch line couplers you get in microwave circuits, it needs a little 50 ohm load on one port, and it takes the input and divides it into 2 equal amplitude outputs, 90 degrees apart. Not particularly interested in the 90 degrees apart, but it's just the way it happens to do it. And then I feed them into a couple of ADE5 mixers on both sides, and another new piece of technology which Akeem was asking me lots of questions about in terms of reliability last night. Silicon Labs produced some lovely little modules. Several years ago, we would have made a local oscillator on 1200 or so megahertz from a crystal and several multipliers, or possibly an oscillator with a big phase-locked loop circuit around it with all the time constants that you would need. Silicon Labs produced these things, SI531 and various other varieties. They're essentially an oscillator up in the 4 gigahertz region and some onboard digital signal processing electronics, which then allow you to select the frequency you want, sort of, if you like, a divide by n type fractional approach where you can get exactly the frequency you want. The lower frequency versions of these, DigiKey in the USA, you type in the frequency you want, they program it, send it through the post to you, absolutely marvelous. These ones, a little bit out of the normal frequency range, so Silicon Labs kindly provided some samples for us to use, and they have to be programmed by the manufacturers. But nevertheless, really simple solution. 3.3 volts on the input, differential output, it's LV Peckel logic stage, AC coupled directly into the mixer, a ring mixer with an isolated local oscillator input, and we've got, I think it's plus 5 or 6 dBm going into that mixer, so it's a really small nice solution for driving a diode ring mixer. After that, it's all fairly standard. Diplexer, 45 megahertz is the first IF, and that comes out here. The whole thing is triple conversion, so we go down from 45 megahertz to 10.7 to 455 kilohertz, and that's nicely, it's a nice solution for what we're trying to do on the spacecraft. So this is the finished receiver. You can get an idea of the size. This is an SMA socket down at the bottom here. The funny shape is to fit the enclosure that we had to produce. So SMA here, filter that you can't see. These are the surface acoustic wave devices just here. A preamp there, another SAW filter there, another preamp, and then this is that ceramic material splitter, which, if you consider these things are maybe a quarter of an inch or so, that's truly tiny for what it actually does. And it's rated at several watts as well. That won't burn out. After that, crystal filter here for 45. I send the signal in different directions because it's the same IF on both channels, so I thought best separate them. So 145 megahertz filter here, that's the command side of the receiver. The transponder side of the receiver is here with a CT-CSS decoder, hardwired for 67 hertz. And one audio output comes out somewhere up here, and the other one down here. And it's got RSSI output, so we can see signal levels. And the command one has a Doppler output, so we can tell if the uplink is actually on frequency or slightly off. So we should be able to see if the tracking of the command uplink is actually on frequency. Okay, so BPSK and FM modulator here. This is a modification of one that we flew in FunCube. It's based on a design by Wouter, PA3WEG. But this time rather simpler in that the input is simply at 145 megahertz. We've got the CMOS version of that Silicon Labs device. Little step-down transformer, local oscillator into here, and as the input of BPSK comes in from the computer, this output sort of wobbles up and down and gives us lovely BPSK with virtually no speed limitation. If we put a megahertz into that, we would have a megahertz, 1 megabit per second output, which is rather nice. One buffer amplifier, and then off to the PA. Speedily through this one. This is almost an identical copy of FunCube. We've got a single surface mount Powerfet. I think it's Toshiba from memory. Input here, linear amplifier, some biasing components on the input to hold the gate at a stable voltage. A diode in there so it tracks the temperature reasonably. Current sensors here, this Skyworks switch, which is rated at about 10 watts, and then the output comes into a low-pass filter, a trap there for 70 sems. We did have a trap there for 70 sems as well, but then we found the 1200 megs harmonic just flies straight through those capacitors, so we had to remove that one. Directional coupler there from Mini Circuits, 25 watts rated component. Haven't seen one fail yet, so that's very good. Power detectors from Analog Devices, and then out to a Maxim chip for the A to D converter. Nice thing about being a radio amateur, you don't have to keep it in a lab. You can take it to the top of a hill and go and have a chat with your chums. So just over a year ago, I took it to the top of Dunstable Downs and chatted to Graham and also Chris Weaver. I think he was a little bit further away. So we did some fairly extensive tests just using a patch antenna. That one didn't work too well. And if you notice, my mag mount taped down with tape. Mag mounts don't tend to stick naturally to aluminium boxes, so a bit of a design fail on that one. But nevertheless, it worked very, very well indeed. Enclosures, we used 3D printing to make the first enclosure because the final version was going to be milled from a solid aluminium block. Having done fit checks with that. We, as you can see, changed a few of the connector positions around to compensate, and then a lovely company in the Midlands under Graham's direction produced this particular milled enclosure, which you'll see later on. Under construction, receiver here, unpopulated computer board here, basically EPS on the right-hand side, fairly large processor in the middle, transmit board in the bottom, and the computer board actually goes over the top of that. So the transmit you can't see when you take the lid off, but it all fits together very nicely within our 1 litre volume we were given by ESA. A little bit of engineering model programming. Make it once, program it about 300 times at the very least, finding all the bugs. And that's now coming along very nicely. And a little earlier this year, I think December, myself, Dr. Bridges from Surrey Space Centre, and one of the best students we've ever had on this project. We've had, I think, 5 degree students working on it. And this chap who's in the audience today is Pete Bartram. Pete's doing an MSc at Surrey Space Centre, and as the deadline for his thesis approaches, the length of time per day he spends working on this satellite is increasing in proportion. So he's the bleary-eyed person who's worked most of this week getting the last bugs out of the system. Okay, that's it for my RF look at ESEO.
Thank you, David. You set me some more challenges, of course, with the data warehouse coming down at those speeds. But that's going to be great fun. It's good to see it's come along so well. It's literally almost the past year or so. Is it accelerated, or is it shorter than
We
that?
did a CDR a year ago, and when we passed the CDR in a teleconference, somebody said to us, "Okay, congratulations, your last 5 years' work has been accepted. Now can we have the hardware in 6 weeks' time, please?" No, sorry.
We don't really have time for questions at this point because we're going to go straight into the next presenter, I believe is coming up on Skype. There is another ESEO presentation right at the end of the colloquium, so we'll leave questions until then, if that's okay.